Hello students, welcome to EPG Pathshala. I am Dr. Anjali Sharma from University of Delhi. Today we are going to discuss about the module Motion in Constant Fields from paper Electromagnetic Theory. So from this module students you may get to know about the following. First, the relativistic motion of a charged particle in a static and uniform electric field. Second, the relativistic motion of a charged particle in a static and uniform magnetic field and expressions for frequency and radius of gyration. Third, motion in combined uniform and static transverse electric and magnetic field and its use as a velocity selector. And lastly, the special case of electric and magnetic field which are equal in magnitude. Motion in uniform and static electric fields. One important field of investigation in electrodynamics is the study of motion of charged particles under the influence of various electric and magnetic fields configurations. Such studies are of immense importance in the designing of particle accelerators, magnetohydrodynamics, ionospheres, and cosmic rays to name a few. We will look at the simplest configurations to begin with, that is, motion in a uniform and static electric field. However, from the very beginning, we will consider relativistic dynamics of the charged particle. Let us say we have a particle of charge Q and mass m passing through a region of uniform and static electric field E. The force acting on such a particle is QE. From Newton's second law, the motion of particle is governed by equation dp by dt equals to QE. So, if we fix the direction of electric field to be along x-axis, that is E is equals to Ex into x cap, let the initial momentum of the particle P naught be in the y direction, that is P equals to P naught into y cap. So our aim is to determine the trajectory of the particle passing through such a region. It is clear that the trajectory will lie in the plane containing the electric field and the initial momentum, that is in the xy plane. The solution is thus straightforward, that is dpx by dt equals to qx, which implies that px equals to qext and dpy by dt equals to 0, which implies that py equals to p naught. Here p naught is a constant and we have chosen the origin of the time so that px equals to 0 at t equals to 0. The relativistic expression for the energy of particle including the rest energy is T is equals to under root of m square c raised to power 4 plus p square c square equals to under root of m square c raised to power 4 plus p naught square c square plus q ext whole square into c square, which is further equals to under root of t naught square plus qextc whole square. Now here T naught being the initial energy including rest energy. The relativistic relation between the kinetic energy, momentum and velocity can be written as V is equals to pc square by t, where p is equals to gamma mv and t is equals to gamma mc square. Thus, V is equals to dx by dt equals to pc square by t. So, on equating the x and y components, dx by dt equals to Vx equals to qexc square t divided by under root of t naught square plus qexct whole square, and dy by dt equals to Vy equals to p naught c square divided by under root of t naught square plus q ext whole square. These equations can be solved readily to obtain xt equals to under root of t naught square plus q ext whole square divided by QEX YT equals to P naught C divided by QEX sin H inverse of QEX CT divided by T naught. This is the equation of the trajectory of the particle in a parametric form in terms of time t. So on eliminating t from the two equations, we obtain x is equals to t naught divided by QEX into cos h of QEXY divided by P naught C. In mathematics, this is the equation of a catenary. This is the shape taken by the uniform chain in gravity whose ends are fixed at the same height. There are certain interesting facts which has to be noted. The force is acting along the x direction, so the y component of the momentum is conserved. In the non-relativistic case, it implies that y component of field is also conserved. In the relativistic case, the mass of the particle increases and hence the y component of the velocity decreases and eventually tends to 0. The x component of velocity tends to a constant c and the force essentially increases the mass of the particle. In the non-relativistic case, the trajectory is well known to be a parabola, and indeed a catenary reduces to a parabola for small y. Motion in uniform and static magnetic field. The force acting on a particle of mass m and velocity v in a magnetic field B is given by F is equals to dp by dt equals to q v cross B. Since the force is always directed normal to velocity, no work is done by the magnetic field, and hence kinetic energy of the particle T is equals to gamma mc square also remains unchanged. So therefore dt by dt is equals to 0. Since the kinetic energy is constant in time, so the magnitude of velocity and hence so is gamma. This leads to considerable simplification of the analysis. So here we can see that gamma remains unchanged. So therefore dp by dt equals to d of m gamma v by dt equals to m gamma dv by dt equals to q v cross B, which implies dv by dt equals to q by gamma m v cross B, which implies dv by dt equals to v cross omega B, where omega B is equals to qb by gamma m equals to qc square B by t. Omega B is called gyration frequency or precision frequency. Taking the magnetic field B to be along the z direction, we have dvz by dt equals to 0, that is vz is equals to constant. The other two equations are dvx by dt equals to v y omega b and dv by dt equals to minus vx omega b. So multiplying the second equation with iota and adding these two, will get d by dt of vx plus iota vy equals to minus iota vx plus iota vy into omega b. This equation has the solution vx equals to a omega b cos omega bt and vy equals to minus a omega b sin omega bt, or v equals to vz into z cap plus a omega b cos omega bt into x cap minus a omega b sin omega bt into y cap. So on integrating, we obtain xt equals to x naught plus vzt into z cap plus a sin omega bt into x cap plus a cos omega b into t y cap. The main features of the motion are: in the xy plane, the particle moves in a circle of radius a called as the radius of gyration. Along the direction of magnetic induction, there is no force and the particle moves with a uniform velocity. The path is a helix of radius a and a pitch angle alpha, which is equals to tan inverse of Vz by omega b a. The magnitude of the gyration radius A depends on the magnitude of magnetic field B and transverse momentum P perpendicular of the particle, where mod of P perpendicular is equals to m gamma into under root of Vx square plus Vy square equals to m gamma A omega b equals to m gamma A qb by gamma m equals to qba. This provides a way to determine the transverse momentum of a charged particle and is of considerable interest in particle physics, where all kinds of stratagems are employed to investigate the properties of particles introduced in various particle reactions. The motion and nature of trajectory is the same in the relativistic as well as the non-relativistic cases. The path is a helix. The only difference is the appearance of the factor gamma in various equations. In particular, the gyration frequency, which is omega b equals to qb by gamma m equals to 1 by gamma into qb by m equals to 1 by gamma omega b nr. Motion in combined orthogonal electric and magnetic fields. We now consider a charged particle moving in a combination of electric and magnetic fields. The especially interesting and important case is one in which the two fields are transverse to each other. For a particle with velocity v, we have a Lorentz force equation and energy change equation, that is dp by dt equals to q into E plus V cross B and dt by dt equals to q v dot E. The second equation follows from the relation between energy and momentum, that is t square equals to p square plus c square, which implies t dt by dt equals to p dot dp by dt equals to q p dot E, which implies dt by dt equals to q by t p dot E. Since energy is no longer constant, the previous approach will not work. We now take an altogether different approach and appeal to Lorentz transformation. The electric and magnetic field together form a tensor and transform under Lorentz transformation as the components of the second rank tensor. Let the given frame of reference be K. Consider the another frame of reference K dash moving with velocity u with respect to the frame K. Then in the frame K dash, the Lorentz force equation and the magnetic field and electric field are transformed to dp dash by dt equals to q into E dash plus V cross B dash, which implies E dash equals to gamma into E plus C beta cross B minus gamma square by gamma plus 1 into beta dot E into beta, and B dash equals to gamma B minus beta cross E by C minus gamma square by gamma plus 1 beta dot B into beta, and beta is equals to U by C. There are three cases to be considered. Electric field divided by C. Remember, E by C has the same direction as B, which is less than, greater than or equal to magnetic field. First case, where mod of E by C is less than mod of B. In this case, we have chosen U is equals to E cross B by B square, which implies that beta equals to E cross B by CB square and mod of beta equals to E divided by CB. Since mod of E divided by C is less than mod of B, therefore mod of beta is less than 1, and this is a valid Lorentz transformation. Then in K dash we have E dash equals to gamma into E plus E cross B by B square cross B minus gamma square by gamma plus 1 into beta dot E into beta equals to gamma into E plus E dot B into B divided by B square minus E minus gamma square divided by gamma plus 1 into beta dot E into beta equals to 0. Since E, B and beta are mutually orthogonal, the trajectory in the K dash frame is thus a spiral around the lines of force. In the original frame of reference K, this gyration around the lines of force is accompanied by a uniform drift normal to the fields. This is often called the E cross B drift. The direction of the drift is independent of the sign of the charge of the particle. This rather strange looking result where the particle drifts in a direction normal to both electric and magnetic field that can be understood in a qualitative way. A particle that starts gyrating along B vector is accelerated by E vector, gains energy and moves in a path with larger radius for roughly half of its cycle. Remember, the radius of gyration is proportional to the transverse momentum. In the other half, E deaccelerates it, causing it to lose energy and so move in a tighter arc. The combination of both two arcs produces a translation normal to both E and B. Now let us study about the velocity selector. Let a particle enter a region of cross electric and magnetic field with mod E less than C times mod B. If the particle enters this region with the speed u is equals to E cross B divided by B square normal to both the fields, then in the K dash frame moving with velocity u with respect to K, the speed of the particle is 0. Since the electric field is also 0 in this frame, there is no force acting on the particle in K dash. Its speeds remain 0 in K dash, which implies that its speeds will remain u in the frame K, which is further implies that the particle will move out undeviated through the crossed E cross B. Suitable entrance and the exit slits will then allow only a very narrow band of velocities around E or B to be transmitted. This is a very useful way of having a velocity selector. Now combined with the momentum selector like deflecting magnet, the E cross B velocity selectors can be extract a very pure and monoenergetic beam with different masses and momenta commonly used in high energy accelerators. Mod of E divided by C is greater than mod of B. In this case, U is equals to E cross B by E square. Now, mod of E by C is greater than mod of B. Therefore, mod of beta is less than 1 and this is again a valid Lorentz transformation. Now, mod of E by C greater than mod of B. Therefore, mod of beta is less than 1 and this is again a valid Lorentz transformation. An analysis similar to the mod of E by C less than mod of B case given in K dash, here B dash is equals to 0 and E dash equals to E by gamma. So in K dash the field is a pure uniform and static electric field. The motion is a catenary with ever increasing velocity. The motion in K can be obtained by using the relativistic velocity transformation law. The special case of equal magnitudes, that is E equals to CB. In this case, it is not possible to make transformation to a frame of reference in which the field is purely electric or purely magnetic. Let the magnetic field B be in the Z direction and the electric field E be in the Y direction. The magnitude of the electric field be denoted by E. Then E equals to EY cap and b equals to half of Ez cap, and dp by dt equals to qe plus v cross b equals to q into ey cap plus vy by c into ex cap minus vx by c into ey cap, or dpx by dt equals to q by c e vy and dpy by dt equals to qe into 1 minus vx by c, and dpz by dt equals to 0, which implies that pz is constant. So if T is the kinetic energy, then dt by dt equals to qv dot E equals to q E vy equals to c dpx by dt, or d by dt of t minus cpx equals to 0. So this implies t minus cpx equals to alpha, where alpha is some constant. So t square minus c square px square is equals to t minus cpx into t plus cpx equals to alpha of t plus cpx. So we have a relativistic relation, that is t square equals to m square c raised to power 4 plus c square into mod of p square equals to m square c raised to power 4 plus c square pz square plus c square into px square plus vy square equals to t dash square plus c square into px square plus py square, where t dash square is equals to m square c raised to power 4 plus c square pz square, which is a constant since pz is also a constant. So from these equations, t dash square plus c square py square equals to t square minus c square px square equals to alpha into t plus cpx. Thus t plus cpx equals to 1 divided by alpha into t dash square plus c square py square. So on solving equation 1 and 2, we get t is equals to c square py square plus t dash 2 divided by 2 alpha plus alpha by 2, and px equals to c square py square plus t dash 2 divided by 2 alpha c minus alpha 2c. So further, t into dpy by dt equals to t qe into 1 minus vx by c is equals to qe into t minus cpx equals to qe alpha. 2qe equals to 2 by alpha into t into dpy by dt equals to 1 divided by alpha bracket t plus cpx plus t minus cpx bracket close into dpy by dt equals to 1 divided by alpha bracket alpha plus t plus cpx bracket close dpy by dt equals to 1 2qe equals to 2 by alpha into t into dpy by dt equals to 1 by alpha bracket t plus cpx plus t minus cpx bracket close dpy by dt equals to 1 by alpha bracket alpha plus t plus cpx bracket close dpy by dt equals to bracket 1 plus t plus cpx by alpha bracket close dpy by dt equals to bracket 1 plus t dash square plus c square py square by alpha square bracket close into dpy by dt equals to bracket 1 plus t dash square by alpha square bracket close dpy by dt plus c square py square by alpha square dpy by dt. So on integrating the last form of the above relation, we have 2qet equals to 1 plus t dash square by alpha square whole into py plus c square divided by 3 alpha square py cube. So to determine the trajectory, we start with dx by dt equals to vx equals to c square px by t which implies dx equals to c square px by t into dt equals to c square px by t into 1 divided by dpy by dt whole into dpy equals to c square by 2 qe alpha into px dpy equals to c square divided by qe alpha bracket minus alpha by 2c plus c square py square plus t dash square divided by 2 alpha c into bracket close equals to c square by q e alpha bracket minus alpha by 2c plus c square py square plus t dash square divided by 2 alpha c bracket close dpy. On integrating this equation, we get x equals to c square by 2e alpha bracket minus alpha by 2c plus t dash square divided by 2 alpha c bracket close py plus c square by qe alpha into c by 2 alpha into 1 by 3 py cube, or x equals to c divided by 2 qe bracket minus 1 plus t dash square by alpha square bracket close into py plus c cube divided by 6 qe alpha square into py cube, and dv by dt equals to vy equals to c square py by t, which implies dy equals to c square py by t into dt equals to c square into py by t into 1 divided by dpy by dt into dpy, which is further equals to c square by qe alpha py dpy. So on integrating, we get y equals to c square divided by 2 qe alpha into py square. Similarly, dz equals to c square divided by qe alpha into pz dpy, which implies that z equals to c square pz divided by 2. Therefore, z equals to c square pz divided by qe alpha py. These formulas determine the motion of particle in parametric form, in which py acts as the parameter. The time dependence is given by equation 3. Thus, the problem is in principle fully solved. The solution looks very unlike what we get for the other two cases that we discussed above, that is E by C less than B and E by C greater than B. So students, let us summarize what we have learnt in this module. The relativistic motion of charged particle in a uniform and constant electric field was studied. The differences from non-relativistic case was discussed. The relativistic motion of charged particle in a static and uniform magnetic field was considered, and the expressions for the radius and the frequency of gyrations were obtained. Next, motion in combined uniform and static transverse electric and magnetic field was discussed. For the case of mod E less than C times mod B, a transformation could be made to another frame of reference in which the field is purely electric in nature, and the solution is thus a catenary in that frame. The motion in the original frame is obtained by applying the law of addition of velocities. In the case of mod E less than C times mod B, a transformation can be made to a frame of reference in which the field is purely magnetic, and the solution is thus similar to that in a pure magnetic field along with a drift in the transverse direction. The use of such a configuration as a velocity selector was described. Finally, the special case of electric and magnetic fields which are equal in magnitude, that is mod E is equals to C times mod B, was discussed and the complete solution was obtained. Thank you.